Tonight, we are going to untangle one of the most misunderstood ideas in all of physics: quantum entanglement. You have probably heard that two particles can be connected across the universe, that measuring one instantly affects the other, no matter how far apart they are. It sounds like faster than light communication. It sounds like it breaks everything we know about how the universe works. Einstein himself called it spooky action at a distance, and he meant that as an insult. But here is what almost nobody tells you. Entanglement is real. It has been confirmed by experiment after experiment. And yet, it does not send a single bit of information faster than light. Not one. The truth about what entanglement actually is, and why it cannot do what people think it does, is stranger and more beautiful than the myth. Before we tuck into this, if you find these deep explorations of how the universe actually works interesting, a quick like or subscribe genuinely helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now, with that all said, settle in and get yourself comfortable. Let's begin. Let us start with something you already understand. Coins. You know how a coin works. You flip it, it lands heads or tails. Before it lands, while it is spinning in the air, you do not know which side it will show. But you understand intuitively that the coin already is one or the other. It is spinning, sure, but it is a physical object with a definite state at every moment. If you could freeze time and look at it mid-air, you would see either heads or tails facing up. The uncertainty is in your knowledge, not in the coin itself. The coin knows what it is. You just do not know yet. Now forget everything about that coin. Because in quantum mechanics, things do not work that way. And understanding why they do not work that way is the first step toward understanding what entanglement really is. In quantum mechanics, a particle does not always have a definite value for a given property before that property is measured. This is not a statement about our ignorance. It is not that the particle secretly has a value and we just have not looked yet. The particle genuinely does not have a definite value. It exists in what physicists call a superposition, a state that encompasses multiple possible outcomes simultaneously, with each outcome having a certain probability of appearing when a measurement is finally made. Let me make this concrete. Think about a property called spin. Spin is a quantum mechanical property of particles. It does not mean the particle is physically spinning like a top, though the name suggests that. Spin is an intrinsic angular momentum, a fundamental property like mass or electric charge. For an electron, when you measure its spin along any particular direction, you always get one of exactly two results: spin up or spin down. There is no in between, there is no 3/4 up. It is always one or the other. Always. But here is the strange part. Before you measure the spin, the electron does not have a definite spin direction. It is not secretly spin up or secretly spin down, waiting for you to check. It is in a superposition of both. The electron's quantum state is described by a mathematical object called a wave function, and that wave function contains both possibilities simultaneously, weighted by probability amplitudes. When you perform a measurement, the superposition resolves into one definite outcome. The electron is now spin up, or it is now spin down. But which one you get is fundamentally random. Not random like a coin flip, where you could in principle predict the outcome if you knew all the forces involved. Random in a deeper sense. There is no hidden mechanism that determines the outcome. The universe itself does not decide until the measurement happens. This sounds bizarre. It should sound bizarre. It goes against everything our everyday experience tells us about how objects behave. When you put a ball in a box and close the lid, the ball does not stop having a position. It stays where you put it. But electrons are not balls. They are quantum objects, and quantum objects follow different rules. Rules that have been tested and confirmed by nearly a century of experiments with extraordinary precision. Superposition is not a theory waiting to be proven. It is one of the most thoroughly verified facts in the history of science. This is the part that troubles people most, because everything in our daily lives behaves classically. You put your keys on the counter and they stay there. They do not exist in a superposition of being on the counter and being in your pocket. A cat is alive or it is dead. A door is open or closed. The world around us seems definite, concrete, solid. Objects have properties whether we look at them or not. That is the classical world. The world we evolved in. The world our brains are wired to understand. But at the level of individual particles, the rules change. An electron is not a tiny billiard ball. It is not a small version of anything you have ever held in your hand. It is a quantum object. And quantum objects behave in ways that have no parallel in everyday experience. This is not because our understanding is incomplete. It is not because we need better instruments or smarter theories. It is because nature operates differently at small scales than it does at large scales. The rules that govern atoms and electrons are fundamentally different from the rules that govern baseballs and planets. Both sets of rules are real. Both are valid within their domains. But they are different. And the quantum rules, the rules that govern the smallest pieces of the universe, include superposition. They include the genuine indefiniteness of properties before measurement. And they include, as we are about to see, entanglement. Now, here is where things start to get interesting. Superposition is weird enough when you are talking about a single particle. But what happens when you have two particles? What happens when those two particles interact or are prepared together in a specific way? That is where entanglement enters the story. And this is where physics goes from strange to genuinely breathtaking. Imagine you have a process that produces two electrons at the same time. Not just any two electrons, but two electrons whose total spin must equal zero because of a conservation law. Angular momentum is conserved in quantum mechanics, just like it is in classical physics. If the system started with zero total spin, then the two electrons that come out of the process must have opposite spins. If one is measured as spin up, the other must be spin down. If the first is spin down, the second must be spin up. The total always adds to zero. But remember what we just said about individual quantum particles. Before measurement, neither electron has a definite spin. Each one is in a superposition of spin up and spin down. So how do you write down the quantum state of this two-particle system? You cannot just say the first electron is in a superposition and the second electron is in a separate superposition, because that would not capture the constraint that their spins must be opposite. The particles are not independent, their fates are linked. Instead, you write down a single wave function that describes both particles together. This joint wave function says something very specific. It says the system is in a superposition of two possibilities. Either the first electron is spin up and the second is spin down, or the first electron is spin down and the second is spin up. Both possibilities exist simultaneously. Neither has been selected yet, but the wave function guarantees that whatever outcome occurs for one particle, the opposite will occur for the other. This is entanglement, right here. This is what it is. Two particles described by a single shared wave function where the possible outcomes for one particle are correlated with the possible outcomes for the other. The particles are not connected by any physical wire or beam or force. There is no energy passing between them. There is no signal jumping from one to the other. They are correlated because they were created together in a process that enforced a relationship between their quantum states. The correlation is built into the wave function from the moment the particles are produced. Let me give you an analogy. Imperfect like all analogies for quantum mechanics, but useful for building intuition. Imagine a factory that produces pairs of gloves and ships them in sealed boxes to two different people. One person always gets the left glove and the other always gets the right glove, but neither knows which one they have until they open their box. When the person in London opens their box and finds a left glove, they instantly know the person in Tokyo has the right glove. No signal was sent. No information traveled from London to Tokyo. The correlation was established at the factory when the gloves were packed. Entanglement has something in common with this. The correlation is established at the source, at the moment the particles are created or interact. But here is where the analogy breaks down, and this is important. In the glove analogy, each glove was always a left or right glove from the moment it was packed. The person just did not know which one they had. The uncertainty was in their knowledge, not in the glove. The glove had a definite state the entire time. In quantum mechanics, this is not what happens. The electrons do not have definite spin values before measurement. They are genuinely in a superposition. Neither electron is secretly spin up or secretly spin down while traveling to the detector. The superposition is real. The indefiniteness is real. And the correlations that emerge when measurements are made are different from anything that could be explained by pre-assigned hidden values. We know this because of experiments. Very specific, very carefully designed experiments that we will discuss later. But for now, the key point is this. Entanglement is like the glove analogy in that the correlation is established at the source. But it is unlike the glove analogy in that the particles do not carry predetermined values. The outcomes are genuinely undetermined until measurement, and yet perfectly correlated when measurements are compared. That combination, correlation without predetermination, is what makes entanglement uniquely quantum. Now, let us look at how entangled particles are actually created in real laboratories, because understanding the physical processes helps demystify what is happening. Entanglement is not some exotic phenomenon that only occurs in thought experiments. It is produced routinely in laboratories around the world. Physicists create entangled particles every single day. One of the most common methods for producing entangled photons is called spontaneous parametric down conversion. Here is how it works. You take a special crystal, typically made of a material like beta barium borate, and you shine a laser beam through it. The crystal has a particular arrangement of atoms that allows something unusual to happen. Occasionally, a single photon from the laser beam interacts with the crystal and splits into two lower energy photons. These two new photons are produced simultaneously from the same event, and because of conservation laws, specifically the conservation of energy and momentum, the properties of the two photons are linked. For example, their polarizations can be entangled. Polarization is the direction in which a photon's electric field oscillates. It is a measurable quantum property, similar in some ways to spin for electrons. The two photons produced by parametric down conversion can emerge in a state where their polarizations are correlated. If you measure one and find it is horizontally polarized, the other will be vertically polarized. If you measure the first and find it is vertically polarized, the other will be horizontally polarized. But before measurement, neither photon has a definite polarization. They are in a joint superposition, described by one shared wave function, just like the entangled electrons we discussed. This process is remarkably reliable. Laboratories can produce millions of entangled photon pairs per second. The photons can then be separated and sent in different directions. You could send one photon through a fiber optic cable to a detector across the room, or across a building, or across a city. Experiments have sent entangled photons to detectors separated by hundreds of kilometers. In 2017, a Chinese satellite called Mikius distributed entangled photons to ground stations 1,200 kilometers apart. The entanglement persisted across that distance. The correlations were exactly what quantum mechanics predicted. That experiment with the Mikius satellite deserves a moment of appreciation, because it represents one of the most remarkable technological achievements in the history of quantum physics. The satellite orbits Earth at an altitude of about 500 kilometers, traveling at roughly 7.6 kilometers per second. As it passes over ground stations in China, it has a window of only a few minutes to distribute entangled photon pairs to receivers on the ground. The photons travel through the vacuum of space and then through the atmosphere, subject to turbulence, absorption, and scattering. The fact that entanglement survives this journey, that the correlations between photons separated by over 1,000 kilometers match the predictions of quantum mechanics with extraordinary precision, is a testament both to the robustness of entanglement as a physical phenomenon and to the ingenuity of the experimental physicists who designed the system. The lead scientist, Jianwei Pan, and his team spent over a decade developing the technology needed to make this work. Their success demonstrated that entanglement is not just a laboratory curiosity confined to optical tables in basement laboratories. It is a feature of the universe that persists across genuinely large distances through real environments under real conditions. It works in the real world, not just in idealized thought experiments. Another common method involves atoms or ions. If you have two atoms that interact, for example through a collision or through the emission and absorption of a photon, their quantum states can become entangled. Imagine two atoms that collide and exchange energy. After the collision, the quantum state of each atom depends on what happened to the other. You cannot describe one atom independently. You need a joint wave function that covers both atoms together. Their properties are now correlated in a way that only makes sense when you consider them as parts of a single quantum system. You can also entangle particles that have never directly interacted through a process called entanglement swapping. In this technique, You start with two separate pairs of entangled particles. Then, you perform a specific measurement on one particle from each pair. This measurement, called a Bell state measurement, has the effect of projecting the two remaining particles into an entangled state, even though those two particles never met, never interacted, and were produced by completely separate sources. This is not science fiction. It's been demonstrated experimentally many times. It sounds almost magical, but it follows directly from the mathematics of quantum mechanics. The key is that quantum correlations are not about physical connections between particles. They are about the mathematical structure of the combined quantum state. This brings us to something essential. Entanglement is not a force. It is not an interaction. It is not a mechanism by which one particle sends a message to another. Entanglement is a property of the quantum state of a composite system. It describes how the information about the system is distributed. When two particles are entangled, the information about their individual properties is not contained in their individual states. It is contained in the relationship between them. This is a genuinely new concept that does not exist in classical physics. In classical physics, if you have two objects, you can always describe each one completely and independently. A billiard ball has a position, a velocity, a spin. You can specify all of these without knowing anything about any other billiard ball. Classical objects are independent entities with their own complete descriptions. Quantum particles in an entangled state are fundamentally different. An entangled electron does not have a complete individual description. If you try to describe just one electron from an entangled pair, you find that its quantum state is what physicists call a mixed state. It looks random. It contains less information than you would expect. The missing information is not lost. It is stored in the correlations between the two particles. You can only access that information by looking at both particles together. This is one of the most profound features of quantum mechanics. It tells us that the universe is not just a collection of independent objects with their own separate properties. At the quantum level, objects can become so deeply correlated that they lose their individuality. They become parts of a larger whole, and the whole contains information that the parts do not. Now, I want to be very careful here because this is where popular descriptions of entanglement tend to go off the rails. When people hear that measuring one entangled particle instantly determines the state of the other, they naturally imagine some kind of faster-than-light influence. They picture one particle sensing what happened to its partner and adjusting itself accordingly. But that is not what happens. Nothing is transmitted. Nothing travels between the particles. No signal, no energy, no force, no influence of any kind passes from one particle to the other at the moment of measurement. What happens is that the shared wave function, which describes the system as a whole, updates. Before measurement, the two particles were described by a joint superposition. After one particle is measured, the superposition resolves. The joint state is now definite. If you measured the first electron and found spin up, the wave function now says the second electron is spin down. But this is a change in the mathematical description of the system. It is not a physical signal traveling through space from one particle to the other. Think of it this way. If I tear a page from a book and send one half to Paris and the other half to Sydney, and the person in Paris reads their half, they instantly know something about the piece in Sydney. They know what is on the other half of the page, but nothing travelled from Paris to Sydney at that moment. The correlation was established when the page was torn. The act of reading one half did not send a signal to the other half. It simply revealed information about a correlation that already existed. Now, I already warned you that classical analogies break down for entanglement, and this one does too. The torn page analogy is essentially the hidden variable picture. The idea that the outcomes were predetermined at the source. And as we will explore later, experiments have shown that the quantum correlations are stronger than anything predetermined values could produce. The universe is doing something more subtle than stuffing predetermined answers into envelopes. But the analogy captures one crucial point correctly. The correlation is established at the source. Nothing needs to travel between the particles at the moment of measurement for the correlation to exist. Let me drive this home with one more concrete example. Imagine a particle physicist who creates an entangled pair of photons in her laboratory in Geneva. She keeps one photon in her lab and sends the other through a fiber optic cable to a colleague in Zurich, about 170 kilometers away. The two photons are now separated by a significant distance, but they share a single quantum state. Their polarizations are correlated. The physicist in Geneva measures her photon's polarization and finds it is horizontal. At that instant, quantum mechanics tells us that the photon in Zurich has vertical polarization. But the physicist in Geneva cannot use this to send a message to Zurich. Why not? Because she could not choose the outcome of her measurement. She got horizontal, but she could just as easily have gotten vertical. The result was random. She had no control over it. And a colleague in Zurich, looking at his own photon, just sees a random result too. He measures vertical polarization, but from his perspective, this is simply a random quantum outcome. He has no way of knowing whether Geneva has measured yet, what measurement she chose to perform, or what result she obtained. His data looks completely random. Perfectly, irreducibly random. The beautiful correlation between horizontal in Geneva and vertical in Zurich only becomes visible when the two scientists get together afterward and compare their results. And that comparison requires ordinary communication. A phone call, an email, a letter carried by a postal worker. Classical communication that travels at or below the speed of light. This is the fundamental structure of entanglement. Correlations established at the source, random individual outcomes at each detector, patterns that only emerge when results are compared using classical communication. No faster than light anything, no signal, no message, no usable information transmitted between the particles at the moment of measurement. You might be wondering, if entanglement does not send signals, why was Einstein so bothered by it? That is a fair question, and the answer reveals something deep about the history of quantum physics. Einstein did not dispute that quantum mechanics made accurate predictions. He accepted the experimental results. What he objected to was the interpretation. He could not accept that particles genuinely lacked definite properties before measurement. He believed that quantum mechanics was incomplete, that there must be hidden variables, pre-existing properties that we simply had not discovered yet, that determined the outcomes in advance. In his view, the entangled particles were like the gloves in sealed boxes. Each one already had a definite state. We just did not know what it was until we looked. Einstein, along with physicists Boris Podolsky and Nathan Rosen, formalized this objection in a famous 1935 paper known as the EPR paper after their initials. The paper argued that if quantum mechanics was complete, if particles really lacked definite properties before measurement, then measuring one particle would instantaneously affect the distant particle. And that, Einstein argued, violated the principle of locality, the idea that physical influences cannot travel faster than light. Since Einstein was deeply committed to locality and to his theory of relativity, he concluded that quantum mechanics must be incomplete. There must be hidden variables. For nearly 3 decades, this remained a philosophical debate. Quantum mechanics worked. Its predictions were confirmed by experiment after experiment. But whether the particles had pre-existing properties or not seemed like a question that could not be tested. It seemed like a matter of interpretation rather than physics. For nearly 3 decades, this remained a philosophical standoff. Both sides could argue their case, but neither could prove the other wrong. The experiments that had been done could not distinguish between the two pictures. It seemed like the question might be permanently unanswerable, a matter of taste rather than science. But as we will see, a single physicist eventually found a way to turn this philosophical debate into an experimental question. And the experiments that followed gave us a definitive answer. An answer that confirmed entanglement is genuinely quantum, and not merely a statistical coincidence. But that story, and the remarkable experiments that settled it, is one we will build toward gradually. So, what is entanglement? Let us summarize what we've established. Entanglement is a quantum correlation between 2 or more particles that arises when those particles are described by a single shared wave function. It is produced when particles interact or are prepared together in a way that links their quantum states. The correlation means that measurement outcomes on the particles are related. If you measure one and get a particular result, you can predict the result of a measurement on the other, but the individual outcomes are random and cannot be controlled. The correlation is only visible when results are compared using classical communication. No signal, no energy, no information passes between the particles at the moment of measurement. Entanglement is not a force. It is not a connection. It is not a wire or a beam or a tunnel through space. It is a feature of the quantum state, a mathematical relationship encoded in the wave function that describes the system as a whole. It arises naturally from the laws of quantum mechanics whenever particles interact in the right way. It has been confirmed by thousands of experiments. It is as real as gravity or electromagnetism. And it is one of the most profound discoveries in the history of physics. Not because it allows faster than light communication, because it does not, but because it reveals that the universe has a kind of connectedness that classical physics never imagined. A connectedness rooted not in signals traveling through space, but in the deep mathematical structure of reality itself. And that structure, what it means, what it allows, and what it forbids, is exactly what we are going to explore next. Now that we understand what entanglement is, a correlation between quantum particles encoded in a shared wave function, we need to tackle the question that trips up almost everyone. If measuring one particle instantly tells you something about the other particle, no matter how far apart they are, how is that not communication? How is that not sending information faster than light? Because on the surface, it really does look like it should be. And the reason it is not is one of the most subtle and important ideas in all of physics. To understand it, we need to look very carefully at what actually happens when a measurement is performed on an entangled particle. Not the popular version, not the simplified version. What actually happens? Let us set up the classic scenario. Two physicists, traditionally called Alice and Bob, are going to perform an experiment. They are in a laboratory together, and they have a source that produces pairs of entangled photons. Each pair is produced in an entangled state where the polarizations are correlated. If Alice's photon turns out to be horizontally polarized, Bob's will be vertically polarized, and vice versa. But before measurement, neither photon has a definite polarization. They are in a joint superposition. Alice takes one photon from each pair. Bob takes the other. Then they separate. Alice goes to a laboratory in one city. Bob goes to a laboratory in another city. They could be 100 kilometers apart. They could be on opposite sides of the planet. They could, in principle, be on opposite sides of the solar system. The distance does not matter. The entanglement persists, regardless of how far apart the particles are taken. Quantum mechanics places no limit on the distance over which entanglement can be maintained. Experiments have confirmed this across hundreds and even thousands of kilometers. Now, Alice and Bob each have a collection of photons. Each photon is one half of an entangled pair. Alice has her halves, Bob has his. They have agreed in advance to measure the polarization of each photon at the same angle. Let us say they both measure along the horizontal-vertical axis. They begin their measurements. Alice measures her first photon. She gets horizontal. She measures her second photon. She gets vertical. Her third photon, horizontal. Fourth, horizontal. Fifth, vertical. She continues through her entire collection, recording each result. When she looks at her list of results, what does she see? She sees a random sequence of horizontal and vertical outcomes. Roughly half horizontal, roughly half vertical. No pattern, no structure, no message, just noise. Pure, irreducible quantum randomness. Now, let us look at Bob. He is in his distant laboratory, measuring his photons at the same time. His first photon gives vertical. His second gives horizontal. Third, vertical. Fourth, vertical. Fifth, horizontal. He too records everything. And when he looks at his list, he sees exactly the same thing Alice sees. A random sequence. Roughly half horizontal, roughly half vertical. No pattern, no structure, no information, just noise. Here's the crucial point. If Alice looks only at her results, she sees randomness. If Bob looks only at his results, he sees randomness. There is nothing in Alice's data that tells her anything about Bob. There is nothing in Bob's data that tells him anything about Alice. Each person, looking at their own measurements in isolation, sees exactly what they would see if the photons were not entangled at all. Just random outcomes with a 50-50 split. Entanglement is completely invisible if you only look at one side of the experiment. The correlations, the remarkable quantum correlations that make entanglement special, only appear when Alice and Bob come together and compare their lists. When they line up their results, photon pair by photon pair, they discover something astonishing. Every time Alice measured horizontal, Bob measured vertical. Every time Alice measured vertical, Bob measured horizontal. The results are perfectly anti-correlated. Every single pair matches the prediction of quantum mechanics exactly. But this comparison requires communication. Alice has to send Bob her list of results, or Bob has to send Alice his, or they have to meet in person. And that communication, the act of sharing their results so they can be compared, happens through ordinary classical means. A phone call, an email, a message carried by radio waves or electrical signals through a cable, all of which travel at or below the speed of light. This is the key insight. The correlations are real. They are physically present in the data, but they are hidden in the data. They are encrypted, if you like, by the randomness. You cannot see the correlations by looking at one side alone. You need both sides, and getting both sides together requires classical communication, which means the correlations, stunning as they are, cannot be used to transmit information faster than light. Let me make this even more explicit, because this is the point where most popular explanations fail. People imagine that Alice could use entanglement to send a message to Bob by choosing what to measure. The idea goes something like this. Alice and Bob agree in advance that measuring horizontal polarization means 1, and measuring vertical polarization means 0. Then Alice chooses her measurements to encode a binary message, and Bob reads out the message by seeing what his photons do. This does not work, and understanding exactly why it does not work is essential. The problem is that Alice's choice of what to measure does not affect what Bob sees. Let us walk through this very carefully. Suppose Alice decides to measure her photon's polarization along the horizontal-vertical axis. She gets a random result. Horizontal or vertical, 50-50. Now suppose instead she decides to measure along a different axis, say the diagonal axis, 45 degrees from horizontal. She still gets a random result. Plus 45 or minus 45, 50-50. Alice can choose her measurement axis. That is something she controls. But she cannot choose the outcome. The outcome is random regardless of which measurement she makes. Now, what happens to Bob? If Alice measures along the horizontal-vertical axis and gets horizontal, then quantum mechanics tells us Bob's photon, if he also measures along the horizontal-vertical axis, will give vertical. If Alice instead measures along the diagonal axis and gets plus 45, then Bob's photon, if he measures along the diagonal axis, will give minus 45. The correlations depend on both Alice's choice of measurement and Alice's outcome, and on Bob's choice of measurement. But here is what matters. From Bob's perspective, no matter what Alice does, his results look the same. If Alice measures horizontal-vertical, Bob's results when he measures horizontal-vertical are 50% horizontal, 50% vertical, random. If Alice instead measures along the diagonal axis, Bob's results when he measures horizontal-vertical are still 50% horizontal, 50% vertical, random. The statistics of Bob's outcomes do not change based on what Alice does. Bob cannot look at his data and determine what measurement Alice chose. He cannot determine whether Alice has measured at all. His data is identical in every scenario. It is always random, always 50-50, always structureless. This is not a coincidence. It is not an accident. It is a deep mathematical feature of quantum mechanics. The randomness of quantum measurement outcomes is not just noise that obscures a signal. It is a fundamental shield that prevents entanglement from carrying information. The randomness is what makes entanglement safe for relativity. It is the reason the universe can have non-local correlations without having non-local communication. Let me try another way of explaining this because it is so important. Imagine you are trying to send a message using entanglement. You want to transmit the word hello to someone on Mars. You have a huge collection of entangled photon pairs. You keep one photon from each pair, and your partner on Mars has the other. Now, to send a message, you need to be able to create a pattern in your partner's data. You need their measurements to come out differently depending on what message you are sending. If you want to send a 1, their data needs to look different than if you want to send a 0. But you cannot do this. No matter what you do to your photons, whether you measure them, do not measure them along one axis or another, rotate them, delay them, or destroy them entirely. The statistics of your partners' measurements remain unchanged. Their data always looks random. You cannot make their data look anything other than random by manipulating your half of the entangled pairs. The entanglement guarantees correlations between the two halves, but those correlations are invisible to anyone who only has access to one half. You need both halves to see the pattern, and assembling both halves requires classical communication. Think about what this means practically. If Alice is on Earth and Bob is on Mars, and they share a collection of entangled particles, Alice cannot send Bob a message using entanglement alone. She can measure her particles, Bob can measure his, but Bob's results look random no matter what Alice does. The only way Bob finds out anything useful is if Alice sends him her measurement results through a classical channel, like a radio transmission. That radio transmission travels at the speed of light. It takes somewhere between 3 and 22 minutes to travel from Earth to Mars, depending on orbital positions. So even though the quantum correlations are established instantly across the distance, the ability to do anything useful with those correlations, to actually learn something, to actually compare results, is limited by the speed of classical communication, which is limited by the speed of light. Let me now address a very common objection, because if you have been thinking carefully, you might have one. People sometimes say, well, what if Alice and Bob agree in advance on their measurement settings? What if they pre-arrange everything? Could they then use the correlations to communicate? Here is the scenario. Alice and Bob agree before separating that they will both measure along the horizontal-vertical axis at exactly noon. They synchronize their clocks. At noon, Alice measures her photon and gets horizontal. She now knows that Bob's photon, measured at the same time, gave vertical. She knows this instantly, without waiting for any signal from Bob. This is true. Alice does instantly know Bob's result, assuming he measured along the agreed axis. But this is not communication from Bob to Alice. Bob did not choose to send a message. The result he got was random. He could not control it. Alice learns what random outcome Bob experienced, but Bob did not choose that outcome. There is no information in a random outcome. Communication requires the sender to be able to choose what to send. If every message you send is random and you have no control over what it says, you are not communicating. You are generating noise. This is a subtle but critical distinction. Knowing what happened is not the same as receiving a message. If I flip a coin in London and you flip an identical coin in Tokyo, and by some magical mechanism your coin always lands opposite to mine, then when you see heads, you know I got tails. But I didn't send you any information. I did not choose tails. The coin chose. There is no message because there is no choice. Communication requires control over the signal, and quantum randomness eliminates that control. Some people push further. They ask, what if Alice does not measure her photon at all? Could Bob somehow detect that Alice did not measure? Could the absence of Alice's measurement leave a trace in Bob's data? If so, Alice could send a binary message. Measure means 1. Do not measure means 0. This also does not work, and the reason is elegant. When Alice does not measure her photon, Bob's photon is in a mixed state. It is described by a statistical mixture of horizontal and vertical polarization, each with 50% probability. When Alice does measure her photon and gets, say, horizontal, then Bob's photon is in a definite state, vertical. But here's the thing. When Bob measures his photon, the statistical outcome is the same in both cases. Whether Alice has measured or not, Bob gets horizontal 50% of the time and vertical 50% of the time. The statistics are identical. Bob literally cannot tell the difference. His data looks exactly the same whether Alice measured or not. This is because the two scenarios, Alice measured and got horizontal versus Alice measured and got vertical, average out to the same statistics as Alice did not measure at all. The quantum mechanical term for this is that the reduced density matrix describing Bob's photon is the same regardless of what Alice does. Bob's local reality is completely unaffected by Alice's actions. This is not a loophole that could be exploited with better technology. It is a mathematical property of quantum mechanics, built into the theory at the deepest level. Let me introduce one more idea that helps solidify this understanding. Physicists often talk about the concept of local realism. Local means that what happens at one location cannot instantly affect what happens at a distant location. Realistic means that particles have definite properties whether we measure them or not. Bell's theorem, which we touched on earlier and will explore in more depth soon, showed that quantum mechanics violates local realism. But it is important to understand exactly which part is violated. Quantum mechanics violates realism. Particles do not have definite values before measurement. The outcomes are not predetermined. This is the part that Einstein objected to, and the part that experiments have confirmed. But quantum mechanics does not violate locality in the sense that matters for communication. No information, no energy, no causal influence travels faster than light. The correlations between entangled particles are non-local in the sense that they cannot be explained by any local hidden variable theory. But they are not non-local in the sense that they allow faster than light signaling. These are different meanings of the word local, and conflating them is one of the most common sources of confusion about entanglement. Here is a useful way to think about it. Entanglement creates correlations that are stronger than anything classical physics could produce over the same distance without communication. That is genuinely remarkable. That is what Bell's theorem proves. But those correlations, strong as they are locked behind a wall of randomness. The correlations exist in the joint statistics of the two measurements. They do not exist in either measurement individually. And accessing the joint statistics requires bringing the two sets of results together, which requires classical communication. It is as if the universe has a rule. You can have non-local correlations, correlations that no classical mechanism could explain, but you cannot use those correlations to send a message. The randomness guarantees this. Every possible scheme for using entanglement to communicate faster than light, and physicists have analyzed many of them over the decades, fails for the same fundamental reason. The sender cannot control their outcomes, and the receiver cannot distinguish between different actions by the sender based on their local data alone. Now, people sometimes propose more creative schemes. What about using many entangled pairs and looking for statistical patterns? What if Alice measures thousands of photons along one axis to send a 1 and along a different axis to send a 0? Could Bob detect the statistical difference? No. And this is important enough to walk through carefully. When Alice measures all her photons along the horizontal-vertical axis, each of Bob's photons collapses into either horizontal or vertical, with 50% probability each. When Alice measures all her photons along the diagonal axis instead, each of Bob's photons collapses into either plus 45 or minus 45. But Bob is measuring along the horizontal-vertical axis. When Bob measures a photon that is in the plus 45 state along the horizontal-vertical axis, he gets horizontal 50% of the time and vertical 50% of the time. When he measures a photon that is in the minus 45 state along the horizontal-vertical axis, he also gets horizontal 50% of the time and vertical 50% of the time. So whether Alice chose to measure along the horizontal-vertical axis or the diagonal axis, Bob's statistics are the same. 50% horizontal, 50% vertical. He cannot distinguish the two scenarios. The statistical distribution of his outcomes is identical regardless of Alice's choice. Even with millions of measurements, the data looks the same. No pattern emerges. No message gets through. This result holds for every possible combination of measurement axes that Alice and Bob could choose. It holds for every type of entangled state. It holds for photons, electrons, atoms, ions, and any other quantum system. It is a universal feature of quantum mechanics. Entanglement creates correlations that are invisible to either party acting alone and visible only when results are compared. I want to emphasize something that often gets lost in these discussions. The randomness that prevents entanglement from being used for communication is not a flaw. It is not a limitation of current technology that we might someday overcome. It is a fundamental feature of quantum mechanics. Quantum randomness is not like classical randomness, where the outcome is determined by hidden factors we simply do not know. Quantum randomness is intrinsic. There is nothing beneath it. There is no deeper layer of deterministic physics that generates the random outcomes. The randomness is bedrock. It is the foundation, not the surface. This randomness is closely connected to another fundamental principle in quantum mechanics, the uncertainty principle. Discovered by Werner Heisenberg in 1927, the uncertainty principle states that certain pairs of properties, like position and momentum, cannot both be precisely known at the same time. The more precisely you know one, the less precisely you can know the other. This is not about the clumsiness of our instruments. It is about the fundamental nature of quantum systems. The properties simply do not have simultaneously precise values. The uncertainty principle and entanglement are deeply connected. Both arise from the mathematical structure of quantum mechanics, specifically from the way quantum states are represented as vectors in a mathematical space called Hilbert space. The same mathematical framework that gives rise to superposition, to uncertainty, to the probabilistic nature of quantum outcomes, also gives rise to entanglement. And the same framework that generates entanglement also guarantees that entanglement cannot be used for faster-than-light communication. The features are interlocked. You cannot have entanglement without randomness, and you cannot have the correlations without the inability to control them. They are two sides of the same quantum coin. Let me take a step back and ask a bigger question. Why does the universe work this way? Why does it allow these strange non-local correlations that nevertheless cannot carry information? This is a deep question, and honestly, no one has a fully satisfying answer. We know that this is how quantum mechanics works. We know the mathematics that describes it. We can predict experimental outcomes with extraordinary precision. But why the universe has this particular mathematical structure, why quantum mechanics takes the form it does rather than some other form, remains one of the open questions in physics. What we can say is that this combination of features, non-local correlations that respect the speed of light for information transfer, is remarkably elegant. It gives the universe a kind of connectedness that classical physics lacks, without undermining the causal structure of space-time. Relativity says that information cannot travel faster than light, and this protects causality. It prevents paradoxes where effects could precede their causes. Entanglement, despite its non-local character, is fully compatible with this. The correlations are there. They are real. They are measurable. But they do not violate causality because they do not transmit information. It is worth reflecting on what a delicate balance this represents. If quantum mechanics were slightly different, if the randomness were not perfectly intrinsic, if there was some slight ability to control measurement outcomes, then entanglement could be used for faster-than-light communication. This would violate relativity and destroy causality. Time travel paradoxes would become possible. The logical structure of the universe would collapse. But quantum mechanics is not slightly different. It is exactly the way it needs to be to maintain this balance. The randomness is exactly strong enough to prevent signaling. The correlations are exactly the kind that cannot be used to transmit messages. It is as if the universe is playing a very precise game, allowing the strangest possible correlations while never crossing the line into actual faster-than-light communication. Whether this is a coincidence or reflects some deeper principle that we have not yet discovered is an open question. Some physicists believe that the structure of quantum mechanics might eventually be derived from more basic principles about information and causality. Others think quantum mechanics is fundamental and cannot be derived from anything simpler. This debate continues, and it is one of the most active areas in the foundations of physics. But for our purposes, the key lesson is clear. Entanglement creates correlations. Beautiful, strange, non-classical correlations that reveal something deep about the nature of reality. But correlations are not communication. Knowing that your coin is anti-correlated with the distant coin is not the same as receiving a message from that distant coin. The correlation exists in the relationship between outcomes, and accessing that relationship requires comparing results, which requires classical communication, which cannot exceed the speed of light. The myth of entanglement as a faster-than-light telephone is appealing because it is dramatic. It makes for great science fiction. The idea that you could send a message instantly across the galaxy by wiggling a particle, that two lovers separated by light years could feel each other's presence through some quantum link, that the universe has a built-in communication network that ignores distance. These are beautiful stories, but they are not how the universe works. The real story is different. It is more nuanced, it is more subtle, and in many ways it is more remarkable, because the real story is that the universe allows correlations that classical physics says should be impossible, correlations that no pre-arranged scheme could replicate, and yet it does so without ever violating the speed of light for actual information transfer. The universe is stranger than the myth, but it is also more disciplined. It knows exactly how far to go and when to stop. And the mechanism that enforces this discipline, the mathematical structure that makes it all work, is what we are going to explore next. We have now seen how entanglement works and why the correlations between entangled particles cannot be used to send messages. But everything we have discussed so far has been built on specific examples. Alice measures this, Bob measures that. The statistics come out random. We walked through particular scenarios and showed that communication fails in each one. But a skeptic might reasonably ask, what about a scenario we have not considered? What about some clever measurement scheme that nobody has thought of yet? Maybe there is a loophole. Maybe there is some exotic manipulation Alice could perform on her particles that would leave a detectable trace in Bob's results. Maybe we just have not been creative enough. This is where the no communication theorem enters the picture. And it is one of the most important results in quantum physics, because it does not just show that specific schemes fail. It proves, mathematically, that no scheme can work. Not now, not ever. Not with any technology, any cleverness, any ingenuity whatsoever. The no communication theorem is a mathematical proof derived from the fundamental axioms of quantum mechanics that demonstrates it is impossible to transmit information using entanglement alone. No local operation performed on one half of an entangled system can produce any observable change in the measurement statistics of the other half. Let me unpack what that means in plain language. When physicists say local operation, they mean anything Alice can do to her particle or particles in her laboratory. She can measure them. She can rotate them. She can entangle them with additional particles. She can put them through any physical process that the laws of quantum mechanics allow. She can be as creative and as sophisticated as she wants. The theorem says that none of these actions, absolutely none, will change what Bob observes when he measures his particles. Bob's measurement statistics will be identical regardless of what Alice does. Not approximately identical. Not close enough that you cannot tell the difference. Mathematically, rigorously, exactly identical. The proof of the no communication theorem relies on the reduced density matrix, the mathematical tool we encountered earlier that describes the state of one part of a larger quantum system. Recall that when you trace out Alice's particle from the joint state of an entangled pair, you get Bob's reduced density matrix, which contains everything needed to predict the probabilities of any measurement Bob might perform. The theorem proves that Bob's reduced density matrix is invariant under any operation Alice performs on her particle. Invariant means it does not change. Alice can do whatever she wants, and Bob's reduced density matrix remains exactly the same. Since Bob's reduced density matrix determines all of Bob's measurement probabilities, and since it does not change no matter what Alice does, Bob's measurement outcomes are completely unaffected by Alice's actions. He cannot detect any difference. He cannot extract any information about what Alice did. The mathematics is airtight. Now, I want to stress something important here. The no communication theorem is not an approximation. It is not a statement about what is practically difficult. It is a mathematical consequence of the structure of quantum mechanics itself. It follows directly from two properties that are built into the foundations of the theory. The first is linearity. Quantum mechanics is a linear theory, meaning that quantum states evolve according to linear mathematical operations. The second is the fact that quantum mechanical probabilities are computed using a specific mathematical rule involving the trace of the density matrix. These two properties together guarantee that local operations on one subsystem cannot affect the measurement statistics of a distant subsystem. This is profound. It means that as long as quantum mechanics is the correct description of nature, and every experiment ever performed suggests that it is, then entanglement cannot be used for faster than light communication. This is not a gap in our technology. It is not a limit of our imagination. It is a mathematical law built into the deeper structure of the physical theory that describes reality. You would have to overturn quantum mechanics itself to get around it. And quantum mechanics is, by any measure, the most successful and precisely tested theory in the history of science. Let me try to explain why this result is so robust by examining a few of the more creative schemes people have proposed for using entanglement to communicate, and showing how each one runs into the no communication theorem. One idea involves cloning. The proposal goes like this. Bob receives his half of an entangled pair. He does not know what state it is in because his local state looks random. But what if Bob could make many copies of his particle? If he could clone it, he could perform many different measurements on the copies, building up a statistical picture of the particle's state. Different states give different statistical patterns when you measure many copies. So if Bob could clone his particle, he could determine its state. And since that state depends on what Alice did, Bob could infer Alice's actions. Communication achieved. The problem is that quantum mechanics does not allow cloning. This is called the no cloning theorem, proven by William Wouters and Wojciech Zurek in 1982. It states that it is impossible to create an identical copy of an arbitrary unknown quantum state. This is not an engineering limitation. It is a mathematical consequence of the linearity of quantum mechanics, the same linearity that underlies the no communication theorem. If you could clone quantum states, you could violate the no communication theorem. But quantum mechanics forbids cloning precisely because it is a linear theory. The two results are connected. They emerge from the same mathematical structure. The no cloning theorem is remarkable in its own right. In classical physics, you can always copy information. You can photocopy a document. You can copy a computer file. You can look at a sequence of numbers and write them down again. Classical information can be duplicated freely, but quantum information cannot. A quantum state is a fragile thing. Measuring it disturbs it. Copying it is impossible. This is one of the fundamental differences between classical and quantum information, and it has enormous implications for fields like quantum computing and quantum cryptography. But for our purposes, the key point is that the no-cloning theorem blocks one of the most obvious routes to using entanglement for communication. Bob cannot clone his particle to determine its state, so he cannot infer what Alice did. Another proposed scheme involves what physicists call superluminal signaling through entanglement swapping. The idea is that Alice could entangle her particle with the third particle, effectively changing which particles are entangled with which. Could this rearrangement of entanglement somehow be detected by Bob? The answer is no. Entanglement swapping changes the global quantum state, the joint state describing all the particles together, but it does not change Bob's reduced density matrix. Bob's local measurement statistics remain the same. He cannot detect that Alice performed an entanglement swap. This is again a direct consequence of the no communication theorem. Any local operation by Alice, including entanglement swapping, leaves Bob's local state unchanged. Yet another idea involves delayed choice experiments. What if Alice waits to decide whether to measure her particle until after Bob has already measured his? Could the timing of Alice's decision retroactively affect Bob's result? Quantum mechanics does include some strange features related to timing and measurement order, and there are famous experiments like the delayed choice quantum eraser that seem to suggest backward in time effects. But when you analyze these experiments carefully, the no communication theorem holds. Bob's measurement results are not affected by Alice's later decision. The apparent retrocausal effects only appear in the correlations, which again are only visible when Alice and Bob compare results using classical communication. The delayed choice experiments are fascinating and genuinely counterintuitive, but they do not enable faster than light communication. Some proposals have involved using quantum fields rather than individual particles. What if Alice manipulates the quantum vacuum in her region of space? Could this create a disturbance that Bob could detect? Again, no. Quantum field theory, the framework that combines quantum mechanics with special relativity, incorporates the no communication theorem at a structural level. In quantum field theory, measurements made in space-like separated regions, meaning regions that cannot be connected by a light signal, are guaranteed to be statistically independent. This is called microcausality, or the principle of local commutativity. It means that the mathematical operators describing Alice's measurements commute with the operators describing Bob's measurements when Alice and Bob are space-like separated. Commutation means the order does not matter. Alice's measurement and Bob's measurement do not interfere with each other. They are independent. This is built into the very foundations of quantum field theory, and ensures that no physical process can transmit information faster than light. Now, let me address something that causes a lot of confusion. The word instantaneous, people often describe the effect of measuring one entangled particle as instantaneously affecting the other. And this language, while common, is deeply misleading. What actually happens when Alice measures her entangled photon? The joint quantum state updates. If the system was in a superposition of possibilities, it resolves into one definite outcome. If Alice gets horizontal, the joint state now says Bob's photon is vertical. This happens immediately in the mathematical description. But does it happen instantaneously in physical reality? This question is harder than it seems. In relativity, the concept of simultaneity is not absolute. Two events that are simultaneous in one reference frame may not be simultaneous in another. If Alice and Bob are far apart, it is not even meaningful to ask whether their measurements happen at the same time, unless you specify a reference frame. In some frames, Alice measures first. In others, Bob measures first. In still others, they measure simultaneously. Relativity tells us that all these descriptions are equally valid. There is no absolute fact about which measurement happened first. This might seem like a problem for quantum mechanics. If it is ambiguous, which measurement happened first, how can we say that Alice's measurement affected Bob's particle? The answer is that it does not matter. The no communication theorem guarantees that the correlations are the same, regardless of the order of measurements. Whether Alice measures first or Bob measures first, or they measure simultaneously, the statistics come out the same. The correlations between their results are identical. Quantum mechanics gives the same predictions regardless of the temporal order of space-like separated measurements. This is a necessary requirement for consistency with relativity, and quantum mechanics satisfies it perfectly. This means there is no physical sense in which Alice's measurement causes Bob's particle to change. There is no sequence of events where a disturbance starts at Alice's location and propagates to Bob's location. There is no signal, no wave, no field disturbance, nothing traveling from one place to another. The correlations exist in the joint state, and they manifest when measurements are compared. But they do not require any physical process connecting the two measurement events. The concept of one measurement affecting the other is a remnant of classical thinking, where correlations between distant events must be mediated by signals. In quantum mechanics, correlations can exist without signals. That is what entanglement is, and the no communication theorem tells us that these signal-free correlations cannot be exploited to transmit information. Let me now step back and appreciate the elegance of this situation. The universe seems to be governed by a beautiful and precise set of rules. On one hand, relativity says that nothing, no object, no signal, no information can travel faster than light. This protects causality. It prevents paradoxes. It gives the universe a coherent causal structure where causes precede effects, and the flow of events makes logical sense. On the other hand, quantum mechanics says that particles can be entangled, sharing correlations that are stronger than anything classical physics allows. These correlations span any distance. They persist no matter how far apart the particles are taken. They are genuinely non-local in the sense that they cannot be explained by any local mechanism. These two principles seem to be in tension. How can you have non-local correlations without non-local signaling? How can the universe allow connections that span light years, while simultaneously forbidding any information from traveling faster than light? The no communication theorem resolves this tension. It shows that the non-local correlations of quantum mechanics are precisely the kind that cannot transmit information. They are hidden behind randomness. They are locked in the joint statistics. They are invisible to any single observer. The universe allows the strongest possible correlations, while still maintaining the absolute ban on faster-than-light communication. This is not just a fortunate coincidence. Physicists have explored this boundary extensively. In the 1990s, researchers including Sandu Popescu and Daniel Rawlich asked a deep question. Quantum correlations are stronger than classical correlations, but are they the strongest possible correlations consistent with the no signaling principle? Or could the correlations be even stronger while still preventing communication? It turns out that yes, mathematically, you can define correlations that are stronger than quantum correlations and still do not allow signaling. These are called Popescu-Rawlich boxes, or PR boxes. They are theoretical constructs that violate Bell's inequality more strongly than quantum mechanics does, while still satisfying the no signaling condition. But these super quantum correlations do not appear in nature. The universe does not use them. Quantum mechanics gives us correlations that are stronger than classical, but weaker than the maximum allowed by no signaling. Why the universe stops at the quantum limit rather than going all the way to the PR box limit is still an open question. Some researchers believe that if correlations were any stronger than quantum mechanics allows, it would have strange consequences for computation and communication. For example, it has been shown that PR box correlations would make all communication problems trivially easy, collapsing the complexity of communication in ways that seem physically unreasonable. This suggests that the quantum limit might be selected by some deeper principle about the nature of computation or information. But we do not yet know what that principle is. What we do know is that the universe has found a sweet spot. Correlation strong enough to be genuinely non-classical, strong enough to defy any explanation based on prearranged hidden variables, strong enough to enable entirely new technologies like quantum computing and quantum cryptography, but not so strong that they break causality, not so strong that they allow faster than light communication. The universe walks a tightrope, and it walks it perfectly. Let me now address one final misconception that comes up repeatedly in discussions about entanglement and the no communication theorem. People sometimes say that entanglement does transmit information, just not usable information. Or they say that it transmits information but not faster than light somehow. Or they suggest that the information is there but encrypted, and we just need to figure out the key. None of these are correct. Entanglement does not transmit information. Period. Not encrypted information, not hidden information, not unusable information. The no communication theorem does not say that the information is transmitted but cannot be read. It says that no information is transmitted at all. Bob's local measurement results contain zero information about Alice's actions. Not a little bit. Not some fraction. Zero. The mutual information between Alice's choice and Bob's local results is exactly zero. This is a precise, quantitative statement. It can be calculated, and it has been calculated. The answer is zero. Always zero. For any entangled state, for any measurement Alice performs, for any measurement Bob performs. 0 bits of information transmitted. This is perhaps the hardest thing for people to accept, because our intuition screams that something must be traveling between the particles. When Alice measures her particle and the distant particle's state is determined, it feels like something happened to that distant particle. Something changed. But what changed is the mathematical description of the system, not the physical reality at Bob's location. Nothing detectable changed at Bob's location. Nothing measurable, nothing observable. Bob's universe is exactly the same regardless of what Alice did. His particle's behavior is indistinguishable. His measurement results are identical. There is no experiment, no matter how sophisticated, that Bob could perform to detect any trace of Alice's actions. This is what the no communication theorem guarantees. Not that communication is difficult, not that it requires special equipment or clever techniques. It guarantees that communication via entanglement is impossible. Fundamentally, absolutely, provably impossible within the framework of quantum mechanics. And this brings us to a deeper point about the nature of physics itself. Physics is not just about what we can do. It is about what the universe allows and what it forbids. The laws of physics are not just descriptions of what happens. They are constraints. They tell us what is possible and what is not. The conservation of energy tells us we cannot create energy from nothing. The second law of thermodynamics tells us we cannot decrease entropy in an isolated system. The speed of light tells us we cannot send signals faster than 300,000 kilometers per second. And the no communication theorem tells us we cannot use quantum entanglement to transmit information. These constraints are not limitations to be lamented. They are the architecture of reality. They define the playing field on which everything happens. Without conservation of energy, the universe would be chaotic. Without the second law, there would be no arrow of time. Without the speed limit, there would be no causality. And without the no communication theorem, entanglement would break relativity, creating a universe where effects could precede causes and paradoxes would be unavoidable. The no communication theorem is not just a technical result buried in physics journals. It is one of the pillars that hold up the logical structure of our universe. It is the reason quantum mechanics and relativity can coexist. It is the reason the universe can have entanglement, one of its most remarkable features, without falling into logical contradiction. It is, in the deeper sense, what makes the universe make sense. Think about what would happen if the no communication theorem were false. If entanglement could transmit information faster than light, then according to relativity, you could use this to send information into the past. This follows directly from the structure of space-time. If you can send a signal faster than light in one reference frame, there exists another reference frame in which that signal arrives before it was sent. This allows the construction of a causal loop, a situation where an event is caused by its own future consequences. You could send yourself a message telling you not to send the message. This is a logical paradox. It is not just counterintuitive, it is logically contradictory. The universe cannot function if logical contradictions are possible. By preventing faster than light communication, the no communication theorem prevents these causal paradoxes. It preserves the logical consistency of the universe. It ensures that causes always precede effects, that the flow of time makes sense, that the universe is a rational, comprehensible place where the laws of logic hold. Some physicists have speculated about what would happen if we discovered a violation of the no communication theorem. If someone found a way to send information using entanglement that violated the theorem's predictions. This would not just be an interesting anomaly. It would mean that quantum mechanics is wrong at a fundamental level. It would mean that our best theory of the microscopic world, verified to extraordinary precision across a century of experiments, has a fatal flaw. It would require a revolution in physics comparable to the revolutions that produced quantum mechanics and relativity in the first place. It would change everything, but no such violation has ever been observed. Every experiment, every test, every measurement is consistent with the no communication theorem. The theorem holds. The universe follows the rules. Let me close this section with a thought about what makes the no communication theorem so beautiful. In mathematics and physics, the deepest results are often those that show why something cannot be done. The impossibility of trisecting an angle with compass and straight edge, proven in the 19th century, revealed deep truths about the nature of algebraic numbers. The incompleteness theorems of Kurt Gödel, proven in 1931, revealed fundamental limits on what mathematical systems can prove about themselves. The no communication theorem belongs in this tradition. It reveals a fundamental limit on what the universe allows. You can have non-local correlations, but you cannot use them to communicate. You can have entanglement, but you cannot exploit it for signaling. The universe gives you one of the most extraordinary phenomena in all of physics, and then it places a precise, elegant, mathematically rigorous boundary around what you can do with it. And that boundary, far from being frustrating, is actually what makes entanglement useful. Because the same properties that prevent entanglement from transmitting information, the randomness, the inability to clone quantum states, the invariance of local statistics under distant operations, are exactly the properties that make entanglement valuable for technologies like quantum cryptography. The security of quantum key distribution, one of the most practical applications of entanglement, relies on the fact that quantum states cannot be copied without disturbing them. An eavesdropper who tries to intercept an entangled particle and measure it will inevitably disturb the entanglement. Alice and Bob can detect this disturbance and know their communication has been compromised. The very features that prevent entanglement from being a telephone are what make it a perfect foundation for secure communication. The universe, it turns out, is not just consistent. It is economical. The same principles that enforce the rules also create the opportunities. The same randomness that blocks signaling enables security. The same structure that preserves causality opens the door to quantum computing. The constraints are not obstacles, they are features. And understanding them, truly understanding them, transforms entanglement from a confusing paradox into one of the most elegant and powerful ideas in all of science. So we have arrived at the heart of the matter. We know what entanglement is. We know that measurement outcomes on entangled particles are correlated but individually random. We know that the no communication theorem mathematically forbids using entanglement to transmit information. But there is still a question lingering in the background, and it is the question that troubled Einstein for the last 3 decades of his life. If entanglement does not send signals, what is actually going on? What does it mean for two particles to be correlated in ways that no classical explanation can account for? And how do we know, really know, that no classical explanation works? This is where Bell's theorem enters the story. And Bell's theorem is not just another result in physics. It is one of the most important discoveries of the 20th century. It took a philosophical debate that had raged for decades and turned it into a question that experiments could answer. It drew a line in the sand between two fundamentally different pictures of reality and gave us a way to determine which one the universe actually uses. Earlier, we encountered Einstein's deep discomfort with entanglement. He believed quantum mechanics was incomplete, that particles must carry definite hidden properties at all times, and that the apparent randomness of quantum outcomes was just a reflection of our ignorance, rather than a feature of reality. In his view, entangled particles were like sealed envelopes. Each one already contained a definite answer from the moment it was created. Measuring the particle just meant opening the envelope. The outcome was never uncertain. We simply had not looked yet. This is called a local hidden variable theory. Local because each particle carries its own information independently, with no need for faster-than-light influences. Hidden because the variables are not directly accessible to us. They are beneath the surface of quantum mechanics, determining the outcomes but not visible in the standard theory. Variable because they can take different values for different particle pairs, explaining the statistical nature of quantum predictions. If local hidden variables were the correct description, entanglement would be entirely mundane. The correlations between measurements would be like the correlations between the gloves in sealed boxes. Predetermined at the source, nothing surprising, nothing non-local, nothing that Einstein would find objectionable. The universe would be fundamentally local and deterministic, and quantum mechanics would be an incomplete description of a deeper, more sensible reality. For nearly 30 years after the EPR paper in 1935, this remained a matter of opinion. Physicists who preferred quantum mechanics argued that hidden variables were unnecessary. Physicists who preferred Einstein's view argued that hidden variables were more philosophically satisfying. But there seemed to be no way to distinguish between the two experimentally. Both pictures made the same predictions for the experiments that had been performed. The debate appeared to be permanently stuck. Then, in 1964, John Stuart Bell, a physicist working at CERN in Geneva, published a short paper that changed everything. Bell asked a deceptively simple question. Do local hidden variable theories and quantum mechanics always make the same predictions? Or are there experiments where they disagree? He found that they disagree. Not for the simple experiments that had been performed so far, where Alice and Bob both measure along the same axis. For those experiments, both pictures give the same predictions. The correlations are the same. You cannot tell the difference. But Bell considered what happens when Alice and Bob measure along different axes. When Alice measures her particle's spin along one direction, and Bob measures his along a slightly different direction, the predictions of quantum mechanics and local hidden variable theories diverge. Specifically, Bell derived a mathematical inequality, a limit on how strongly the measurement results of Alice and Bob can be correlated if local hidden variables are the correct description. This inequality, now called Bell's inequality, places an upper bound on the strength of correlations in any local hidden variable theory. No matter what hidden variables the particles carry, no matter how cleverly they are assigned, the correlations cannot exceed a certain value. But quantum mechanics predicts that entangled particles can produce correlations that exceed Bell's inequality. Quantum mechanics predicts stronger correlations than any local hidden variable theory can produce. Not just slightly stronger, measurably, detectably, unambiguously stronger. This was revolutionary. It meant that the debate between Einstein and quantum mechanics could be settled by experiment. You prepare entangled particles, you send them to two distant detectors, you measure them along carefully chosen angles, you calculate the correlations, and you check whether the correlations respect Bell's inequality or violate it. If they respect it, Einstein was right, and hidden variables are the explanation. If they violate it, quantum mechanics was right, and hidden variables cannot explain what is happening. The first serious experimental test of Bell's inequality was performed by John Clauser and Stuart Friedman at the University of California, Berkeley, in 1972. They produced entangled photons and measured their polarizations at different angles. The results violated Bell's inequality. The correlations were stronger than any local hidden variable theory could explain. Quantum mechanics was confirmed, but the experiment had limitations. There were loopholes, subtle ways in which the results could potentially be explained without abandoning local hidden variables. Maybe the detectors were not efficient enough, and the missed photons were biased in a way that mimicked a Bell violation. Maybe the measurement settings were not truly random, and some hidden influence was coordinating the choices. These loopholes, while unlikely, could not be completely ruled out. In 1982, Alain Aspect and his colleagues in Paris performed a more sophisticated experiment that closed some of these loopholes. They used a clever setup where the measurement angles were changed while the photons were still in flight, so that no signal traveling at the speed of light could carry information about one detector's setting to the other detector in time to influence the result. The results again violated Bell's inequality, and more convincingly than before. Over the following decades, experimenters closed one loophole after another. Detection efficiencies improved. Random number generators were used to choose measurement settings. The distances between detectors were increased. Each new experiment confirmed the same result. Bell's inequality was violated. Quantum mechanics was right. It is worth pausing to appreciate the human story behind these experiments, because it is a story of persistence against skepticism. When John Clauser first proposed testing Bell's inequality in the late 1960s, many physicists thought it was a waste of time. The mainstream view was that quantum mechanics was obviously correct, that hidden variables were a philosophical curiosity not worth testing, and that anyone who spent time on the question was not doing serious physics. Clauser struggled to get funding and support. He built much of his apparatus himself, improvising solutions to engineering problems that no one had tackled before, because no one had tried the experiment before. Senior physicists advised him against pursuing it. Colleagues told him it would be a career dead end. He did it anyway. Clauser and Friedman's 1972 experiment was groundbreaking but imperfect. The detectors were inefficient, catching only a small fraction of the photons produced. This opened the detection loophole. Maybe the photons that were detected were not representative. Maybe the ones that slipped through had different properties. It was unlikely, but it could not be ruled out. Alain Aspect's experiments a decade later were more sophisticated. Aspect introduced a crucial innovation. He used acousto-optic switches to change the measurement settings while the photons were already in flight. This meant that the choice of what to measure was not made until it was too late for any signal, even one traveling at the speed of light, to carry information about that choice from one detector to the other. This went a long way toward closing the locality loophole, making it far harder to argue that the two measurements were not genuinely independent. But because aspects switching was periodic rather than truly random, a determined skeptic could still argue that some hidden pattern coordinated the results. The loophole was narrowed dramatically but not fully sealed. No hidden signal could coordinate them. Aspects' results were cleaner and more decisive. Bell's inequality was violated by a wide margin. The quantum predictions were confirmed with high statistical confidence, but the detection loophole remained open. The detectors still missed many photons. Closing both loopholes simultaneously turned out to be extraordinarily difficult. You needed detectors efficient enough to catch nearly every photon, eliminating the detection loophole, and you needed the detectors far enough apart with fast enough switching to eliminate the locality loophole. For decades, every experiment that closed one loophole left the other open. It was like trying to patch two holes in a boat at the same time while the boat is sinking. Fix one and water comes through the other. It took over 4 decades of incremental progress before the technology existed to close both loopholes in a single experiment. When it finally happened in 2015, it was the culmination of a quest that had begun with Bell's 1964 paper and Clause's lonely experiment in a basement laboratory. In 2015, 3 independent experiments finally closed all the major loopholes simultaneously. These experiments, performed by groups in the Netherlands, Austria, and the United States, are considered the definitive tests of Bell's inequality. They left essentially no room for local hidden variable theories. The correlations between entangled particles are genuinely stronger than classical physics allows. The particles do not carry predetermined answers. The outcomes are not decided in advance. Entanglement is real, and it is fundamentally quantum. For these contributions to our understanding, John Clause, Alain Aspect, and Anton Zeilinger were awarded the Nobel Prize in Physics in 2022. The citation specifically recognized their experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. It was a recognition that Bell's theorem and its experimental confirmation rank among the most important achievements in the history of physics. Now, here is the part that is absolutely critical and that most popular accounts get wrong. Bell's theorem proves that the correlations between entangled particles cannot be explained by local hidden variables. It proves that the universe is not locally realistic in the classical sense, but it does not prove that anything travels faster than light. It does not prove that measuring one particle instantaneously affects the other. It does not prove superluminal signaling or communication. What Bell's theorem shows is that the correlations are non-local. They cannot be explained by any mechanism where each particle independently carries its own predetermined values. But non-local correlations are not the same as non-local signaling. This distinction is subtle but essential. The correlations violate Bell's inequality, meaning they are stronger than any local mechanism could produce. But they still satisfy the no communication theorem, meaning they cannot be used to send information faster than light. The universe, according to the experiments, is non-local in its correlations, but local in its information transfer. These two properties coexist. They are compatible, They do not contradict each other. You can have correlations that defy any local explanation while still obeying the speed of light for all practical communication purposes. Think of it this way. Bell's theorem eliminates the comfortable classical explanation for entanglement. It proves that the correlations are not just pre-arranged coincidences. Something genuinely quantum is happening. But the no communication theorem simultaneously proves that whatever is happening, it does not allow information to travel faster than light. Both results are true, both are proven, and together they paint a picture of a universe that is stranger than Einstein wanted to believe, but not as strange as the popular myths suggest. Einstein was wrong about hidden variables. The experiments have shown this conclusively. Particles do not carry predetermined values. The outcomes are not decided in advance. But Einstein was right about one crucial thing. Entanglement does not allow faster than light communication. Relativity is safe. Causality is preserved. The speed of light remains the ultimate speed limit for information transfer. The universe turned out to be more quantum than Einstein hoped, but it is also more relativistic than the popular mythology suggests. So, where does this leave us? What picture of reality does quantum entanglement paint? The honest answer is that physicists are still debating this. The mathematics of quantum mechanics is clear and unambiguous. It tells us exactly what predictions to make, and those predictions are confirmed by experiment with extraordinary precision. But what the mathematics means, what it tells us about the underlying nature of reality, is still an open question. Some physicists favor an interpretation where the wave function is a real physical thing, a field-like entity that exists in a high-dimensional mathematical space and collapses when measurements are made. Others favor an interpretation where the wave function is a tool for calculating probabilities, not a description of physical reality. Still others favor interpretations where the wave function never collapses, but instead the universe splits into branches, with each possible outcome occurring in a different branch. What all these interpretations agree on is the physics. They all make the same predictions. They all respect Bell's theorem. They all satisfy the no communication theorem. They all agree that entanglement is real, that the correlations are genuinely quantum, and that no information travels faster than light. The interpretations differ in their stories about what happens behind the scenes, but they agree on everything that is experimentally testable. For our purposes, what matters is the physics, not the interpretation. And the physics is clear. Entanglement produces correlations that are non-classical and non-local, but these correlations cannot be used for faster-than-light communication. The universe allows entanglement while preserving relativity. Both coexist, and the mathematical framework that describes them is consistent and well-tested. Now, having spent all this time explaining what entanglement cannot do, let me talk about what it can do. Because entanglement is not just a philosophical curiosity, it is a physical resource with real, practical applications. Some of these applications already exist, others are being developed, and all of them arise precisely because of the unique properties we have discussed, the properties that make entanglement both powerful and constrained. The first and most developed application is quantum key distribution. This is a method for two parties to share a secret key, a random string of numbers that could be used to encrypt and decrypt messages. The security of the key is guaranteed by the laws of quantum physics, not by the difficulty of solving mathematical problems. In classical cryptography, security typically depends on the assumption that certain mathematical operations are hard to reverse. For example, it is easy to multiply two large prime numbers together but very hard to factor the result back into its components. This is the basis of the RSA encryption system that secures most internet communication today. But if someone builds a powerful enough quantum computer, they could potentially factor large numbers quickly, breaking RSA encryption. Quantum key distribution avoids this problem entirely. The security comes from quantum mechanics itself. When Alice and Bob share entangled particles and measure them, they can generate a shared random key. The randomness of quantum measurements guarantees that the key is truly random, not generated by an algorithm that could be predicted. And the no-cloning theorem guarantees that any eavesdropper who tries to intercept the entangled particles will disturb them in a detectable way. Alice and Bob can check for this disturbance by comparing a small subset of their results. If the correlations match what quantum mechanics predicts, they know their key is secure. If the correlations are off, they know someone tried to listen in. This has been demonstrated experimentally over distances of hundreds of kilometers using fiber optic cables. The Misseus satellite, whose entanglement distribution experiments we discussed earlier, has also demonstrated quantum key distribution between its ground stations. Several countries and companies are developing quantum communication networks based on this technology. It is not science fiction. It is happening now. The second major application is quantum teleportation. Now, this is perhaps the most misunderstood concept in all of quantum information. Quantum teleportation does not teleport matter. It does not teleport energy. It does not teleport information faster than light. What it does is transfer a quantum state from one particle to another, using entanglement and classical communication together. Here is how it works. Alice has a particle in an unknown quantum state that she wants to transfer to Bob. Alice and Bob also share an entangled pair of particles. Alice performs a special measurement on her unknown particle and her half of the entangled pair. This measurement gives her a result, 2 bits of classical information, which she sends to Bob through an ordinary classical channel. When Bob receives these 2 bits, he performs a specific operation on his half of the entangled pair, and his particle ends up in exactly the state that Alice's original particle was in. The quantum state has been transferred from Alice's particle to Bob's particle. But notice what happened. Alice had to send 2 bits of classical information to Bob for the teleportation to work. Without those 2 bits, Bob's particle is in a random state. He cannot reconstruct the original quantum state without the classical information. And that classical information travels at or below the speed of light. So quantum teleportation does not violate relativity. It does not send anything faster than light. It uses entanglement as a resource, combined with classical communication to transfer a quantum state. The entanglement provides the correlations. The classical communication provides the key to unlock those correlations. Neither one alone is sufficient. Let me walk through quantum teleportation more carefully because the details matter and the name is so misleading that almost everyone gets the wrong picture. Imagine Alice has a single photon in a particular quantum state. Maybe it has a specific polarization, some particular combination of horizontal and vertical that encodes quantum information. Alice does not know exactly what this state is. She cannot measure it to find out because measuring it would destroy the superposition. She cannot copy it because the no cloning theorem forbids that. But she wants Bob, who is far away, to have a photon in exactly the same quantum state as hers. Here is what they do. Before starting, Alice and Bob each take one photon from an entangled pair. Alice now has 2 photons in her laboratory. The one whose state she wants to teleport, call it photon A, and her half of the entangled pair, call it photon B. Bob has the other half of the entangled pair, photon C. Alice performs a special joint measurement on photons A and B together. This measurement, called a Bell state measurement, entangles photon A with photon B, and in doing so destroys the original quantum state of photon A. The state is gone from Alice's laboratory, but the measurement gives Alice a result, one of 4 possible outcomes, which she records. Alice then sends this result to Bob using a classical channel. A phone call, a radio signal, anything that travels at or below the speed of light. When Bob receives Alice's 2 bits of classical information, he knows which of 4 simple operations to perform on his photon C. He applies the operation, and photon C is now in exactly the quantum state that photon A was in before Alice measured it. The state has been transferred from photon A to photon C without either the state or any physical object traveling between Alice and Bob. Notice what did not happen. No photon flew from Alice to Bob. No matter was transported. The original photon A is still in Alice's laboratory, but its quantum state has been destroyed by the Bell measurement. The state now exists only on photon C in Bob's laboratory. The quantum information moved, but it moved through a combination of pre-shared entanglement and classical communication. And the classical communication is the bottleneck. Without it, Bob's photon is useless. He cannot reconstruct the state without knowing Alice's measurement result. So the overall speed of teleportation is limited by the speed of classical communication. The speed of light, at most. This is why physicists are careful to call it quantum state teleportation, rather than just teleportation. It is the state that moves, not the particle, and it moves at the speed of light, not faster. Quantum teleportation has been demonstrated experimentally many times over distances ranging from a few meters to over 1,400 kilometers using satellite-based experiments. It is a real phenomenon with real applications. It is essential for quantum networking, where quantum computers at different locations need to share quantum states. But it is not the Star Trek transporter. It does not move objects. It moves information about quantum states, and it does so at the speed of classical communication, not faster. The third major application is quantum computing. Quantum computers use the principles of superposition and entanglement to perform certain calculations much faster than any classical computer could. The key idea is that a quantum computer can process many possibilities simultaneously because its quantum bits, called qubits, can be in superpositions of 0 and 1 at the same time. When qubits are entangled, the computational power increases exponentially because the entanglement creates correlations between the qubits that allow the computer to explore many solution paths at once. Quantum computers are not faster than classical computers at everything. For most everyday tasks, A classical computer is just as good or better. But for certain specific problems, quantum computers offer enormous advantages. Factoring large numbers, which is the basis of much of modern encryption, is one example. Simulating quantum systems, which is crucial for drug design and material science, is another. Searching unstructured databases, solving optimization problems, and modeling complex chemical reactions are all areas where quantum computers could provide breakthroughs. As of today, quantum computers are still in their early stages. The largest quantum processors have a few thousand qubits, but these qubits are noisy and error-prone. Building a large-scale, fault-tolerant quantum computer remains one of the greatest engineering challenges of our time. But progress is being made rapidly. Major technology companies, startups, and governments around the world are investing billions in quantum computing research. The theoretical foundation is solid. The engineering is what needs to catch up. Entanglement is the fuel that powers quantum computing. Without entanglement, a quantum computer would be no more powerful than a classical one. It is the correlations between qubits, the non-classical relationships that entanglement creates, that give quantum computers their advantage. Every time you hear about a quantum computing breakthrough, you are hearing about the practical application of the very phenomenon we have been discussing. There is also quantum sensing. Entangled particles can be used to make measurements with precision that exceeds what is possible with classical methods. By exploiting the correlations between entangled particles, scientists can reduce the noise in their measurements and achieve sensitivities that would otherwise be impossible. This has applications in medical imaging, navigation, geological surveying, and fundamental physics research. Gravitational wave detectors, for instance, are exploring the use of quantum entanglement to improve their sensitivity beyond the current limits. And there is fundamental research. Entanglement is at the heart of some of the deepest questions in physics today. The relationship between quantum mechanics and gravity, the two pillars of modern physics, remains one of the great unsolved problems. Recent work has suggested that entanglement might play a role in the structure of space-time itself. The physicist Juan Maldacena and others have proposed connections between entanglement and the geometry of space, suggesting that the fabric of space-time might be woven from entanglement. This idea, sometimes summarized as the slogan that entanglement equals geometry, is speculative and far from proven. But it suggests that entanglement might be even more fundamental than we currently realize, not just a curious quantum phenomenon, but a building block of reality itself. Let me now bring everything together. We have taken a long journey through one of the most misunderstood topics in all of science. We started with the basics: quantum superposition, the idea that particles do not have definite properties until they are measured. We saw how two particles can become entangled, sharing a single quantum state where their properties are correlated. We learned that entanglement is not a force or a signal or a connection. It is a property of the quantum state of a composite system, arising from how the particles were prepared or how they interacted. We then explored what happens when entangled particles are measured. The outcomes are individually random. Neither Alice nor Bob sees anything other than noise when looking at their own results. The correlations only appear when results are compared. And that comparison requires classical communication that travels at or below the speed of light. Entanglement does not transmit information. The randomness of quantum outcomes is the shield that prevents it. We examine the no communication theorem, the mathematical proof that no local operation on one half of an entangled system can affect the measurement statistics of the other half. This result is not a technological limitation. It is a consequence of the mathematical structure of quantum mechanics. It holds for all possible measurements, all possible manipulations, all possible entangled states. It is absolute. We explored Bell's theorem and the experiments that confirmed it. These experiments showed that the correlations between entangled particles are stronger than any local hidden variable theory can produce. The universe is genuinely quantum. Particles do not carry predetermined answers. The outcomes are not decided in advance, but crucially, these same experiments confirm that no information travels faster than light. The correlations are non-local. The signaling is not. Both things are true simultaneously. And we looked at what entanglement is actually good for. Quantum key distribution, quantum teleportation, quantum computing, quantum sensing, real technologies with real applications, all built on the unique properties of entanglement. Properties that arise precisely because of the constraints the universe imposes. The randomness that prevents signaling enables security. The correlations that defy classical explanation power, quantum computation. The constraints are the features. Now, I want to leave you with something to think about, because the story of entanglement is not just a story about physics, it is a story about how the universe works at the deepest level. And what it tells us is remarkable. The universe allows connections between particles that span any distance. Two photons created together in a laboratory can maintain their quantum correlation whether they are separated by a meter or a million kilometers. These correlations are real, physical, and measurable. They have been confirmed by experiment after experiment, across decades of increasingly precise tests. The universe is, in some deep sense, more connected than classical physics ever imagined. But the universe is also disciplined. It allows these connections while simultaneously preventing them from being used to send messages faster than light. It preserves causality. It maintains the logical structure of space-time. It ensures that causes precede effects and that the flow of events makes sense. The universe walks a tightrope between non-local correlations and local information transfer, and it walks it flawlessly. This tells us something profound about the nature of reality. The universe is not simply a collection of independent objects sitting in space, each minding its own business. At the quantum level, objects can become intertwined in ways that defy any classical description. Their fates can be correlated in ways that no prearranged agreement could explain. The information about the system is not contained in the parts. It is contained in the relationships between the parts. The whole is more than the sum of its pieces. And yet, this interconnectedness does not turn the universe into chaos. It does not allow paradoxes. It does not break the rules. The universe has found a way to be deeply connected without being causally confused. Entanglement is the mechanism of that connection, and the no communication theorem is the guardrail that keeps everything consistent. Einstein called entanglement spooky action at a distance because he thought it implied that measuring one particle must physically affect the distant partner. He thought this was absurd, and in a sense, he was right to be suspicious. There is no action at a distance. There is no physical influence traveling faster than light. What there is instead is something more subtle, a correlation that exists in the fabric of the quantum state itself, a relationship that was written into the mathematics when the particles were created, and that reveals itself, piece by piece, when measurements are compared through ordinary means. Entanglement is not spooky. It is not magical. It is not mystical. It does not connect minds. It does not transmit feelings. It does not allow telepathy or faster than light communication or any of the other extraordinary claims that popular culture has attached to it. What it does is far more interesting than any of those myths. It reveals that the universe has a structure that classical physics never suspected. A structure where correlations can exist without signals, where connection does not require communication, and where the deepest relationships between particles are encoded not in what they do individually, but in what they do together. That is what quantum entanglement really is. Not a telephone across the cosmos, not a violation of Einstein's relativity, not a loophole in the laws of physics. It is a feature of those laws, a feature that tells us the universe is both more connected and more disciplined than we ever imagined. More connected because entanglement links particles across any distance in ways that no classical mechanism can replicate. More disciplined because even these extraordinary connections cannot break the speed of light for information transfer. The universe gives us something remarkable and then sets precise boundaries around it. And within those boundaries, an entire revolution in technology and understanding is unfolding. The next time someone tells you that quantum entanglement allows faster than light communication, you will know the real story. The correlations are real. The connections are genuine. But no message travels between the particles. No signal. No influence. No information. The universe is stranger than the myth, but is also more consistent. And that consistency, that precise balance between connection and constraint, between the quantum and the relativistic, is one of the most beautiful things physics has ever revealed. So tonight, if you step outside and look up at the stars, remember this. Every photon of starlight that enters your eye is a quantum object. It has properties that are described by quantum mechanics. And somewhere in laboratories around the world, physicists are creating pairs of photons whose fates are intertwined by entanglement, sending them across cities, across countries, across the gap between Earth and orbiting satellites, testing the correlations, confirming the predictions, building the technologies that entanglement makes possible. The quantum revolution is happening right now, built on a phenomenon that Einstein doubted, and that the universe has proven to be one of its most fundamental features. Entanglement does not break the speed of light, but what it does is in many ways more profound. It shows us that the universe is woven together at a level deeper than space and time, that particles created together share a bond that distance cannot diminish, that the information about reality is stored not in individual objects, but in the relationships between them, and that even the strangest features of quantum mechanics respect the rules that keep the universe coherent and comprehensible. That is the real story of quantum entanglement. Not faster than light, not spooky, not broken, Beautiful, precise, and profoundly, unmistakably real. Thank you for joining me on this journey through one of the most fascinating ideas in all of physics. If you found this exploration valuable, a like or subscribe would mean a lot. It helps this channel keep going and helps me keep making these deep dives into how the universe really works. And remember, the universe is stranger and more wonderful than any myth about it. The truth, when you take the time to understand it, is always more extraordinary than the fiction. Good night. And may you never think about entanglement the same way again.